Engineering Innovations, the official podcast of Purdue University's Elmore Family School of Electrical and Computer Engineering. I'm Kristin Malavenda. Today we're talking about something Einstein once called spooky action at a distance. It's quantum entanglements, and how that strange physics is now being engineered into real-world technology. Our guest is Joseph Luken, Associate Professor in Purdue ECE, and also a recipient of the Presidential Early Career Award for Scientists and Engineers. That's the highest honor the U.S. government gives to early career researchers. Joe's work focuses on quantum communication networks, the building blocks of what many call the quantum internet. So what does that actually mean? And how close are we? And what still stands in the way? That's what we'll be talking about today. Joe, thanks so much for joining me today.
Thanks, Kristin.
So let's start out with some of the basics. What's the difference between the internet we're using today and the quantum internet?
Well, the first difference is the quantum internet doesn't exist yet, so that's the easy answer. But the main difference is in the current internet, we're transmitting information in terms of bits. I mean, that's been the most effective way. Digital communication, zeros and ones, and that's how we all talk to each other, how we communicate. The quantum internet, what we're envisioning for the future, is really the transmission of qubits. So these are quantum bits, or qubits for short. And what's so interesting about qubits is they're not in 0 or 1. They're in 0 and 1 simultaneously in some quantum wave function. And so it's been shown for many things in quantum information, in communications, computing, sensing, how these qubits offer a much richer variety of processing application. I mean, you can think of it as kind of looking at 0 and 1 simultaneously in a superposition, and you have many of these qubits, you can have more superposition. So that is what the quantum internet should do. Just as today on the classical internet, really what we're saying is I want to get my bits to you wherever you are in the world.
Yeah.
Now I want to get qubits to you wherever you are in the world. And because qubits are so much more fragile, more difficult to create, control, sustain than digital information. I like to think of digital information, I can get a piece of paper and just write it down.
Yeah.
And it's there, at least in principle. You can't do that with quantum information. And so really what we're looking to do with the quantum internet is to elevate our classical communications infrastructure so that we can get qubits anywhere on Earth.
Okay.
And entanglement as well, which I know we'll be talking about in this podcast as well. Get entanglement between any 2 points on Earth. So we are not there yet, but that is what the quantum internet will do, and that will be the heralding of when we have it, is when I can say anybody on this huge network can get qubits and entanglement.
All right, there you go. Well, I've heard you describe networking as the glue for scaling quantum systems. What does that mean?
So in every application that people are looking at for quantum information, and people typically divide it into like 3 pillars. One would be communications, which is close to networking, but I like to think of it as distinct. Quantum sensing and quantum computing. All of these applications use qubits or other types of quantum systems to get some type of improvement over what we can do today. And looking analogously at where we are in classical systems, like say classical supercomputers, they don't work by having way better CPUs than we have in our personal machines.
Right.
They work by connecting them together. And so networking is critical for getting supercomputing, for example. And we see a similar thing in the quantum space as well. So if we have a quantum computer, maybe it's a cryostat, super expensive, you got to cool it to millikelvin temperatures, and you can fit so many qubits in there. And then it's like, oh, darn, I need more. What do I do? Well, building a bigger cryostat, I mean, that's one way, but maybe a better way is to get a second cryostat and connect it with say, optical fiber, and if you can get those interfaces to work. So that's an example of networking being the glue, gluing 2 quantum computers together. And I think what I want to emphasize with that for networking is there are some applications where you need networks. And so like if I literally need to do something with someone else who's not in my location, I absolutely need a network. And so that is something where it's a glue to enable quantum applications on a scale. But I think it's also important to realize it doesn't have to be long distance either. And I think of that in terms of like the quantum data center type idea. Really, we need the network, not because we're far apart, but just because we have different units that we want to connect and scale. So I think, although there are certainly different viewpoints in quantum computing, I mean, there's all sorts of platforms being explored, but I think most researchers believe whatever their favorite platform is, whether it's superconductors or ion traps or neutral atoms, I think they all believe that they will need to have a network to scale it up. And so that's where the glue of quantum networking will be critical, I think, to get these desired quantum advantages.
So I mentioned the quote from Einstein in the introduction. Why did Einstein struggle with entanglement?
So it's a really fascinating story. So entanglement, when you think about the development of quantum theory, entanglement really emerged as a mathematical construct. Like, we have the theory of quantum mechanics, and we can write different states down following that theory. So a lot of the early researchers in quantum started exploring what are some of these states, what do they look like? And you could draw states that are entangled with each other, meaning that, say, one particle, thinking in a qubit term, could be a 0 or 1, but if it's a 0, then the other particle is also a 0.
Okay.
And if it's a 1, the other particle is also 1. And we have these correlations classically. I mean, we can imagine that, well, if I'm in my office, maybe someone else is in his office, and if we're not in office, if we had some agreement or something like that to coordinate that. But it turns out that quantum mechanically, it's actually very different. Like, we can't use those simple analogies. And so Einstein noted these types of states, and what he pointed out was that this leads to some strange paradoxes. So it seems like if you took your entangled particles and you say, let's say one to the other side of the world and keep one here, and then I do a measurement on my particle, according to the quantum theory of measurement, the other particle on the other side of the world is going to instantaneously collapse into some quantum state.
Okay.
And of course, Einstein, what's he perhaps best known for is relativity. Yeah. He's like, we can't, nothing can happen instantaneously. We have
it doesn't fit with his knowledge of the world.
That's right. We have the speed of light, right? You have to have some type of communication over that distance, or some way to propagate the answer, the result of whatever my measurement was to the other side of the world. And so he pointed this out, and he called it spooky action at a distance. And he didn't think, at this time, it's not as though he thought quantum mechanics was wrong, or he certainly didn't think relativity was wrong. When he was thinking, we're missing something.
Yeah.
There's got to be more to the theory that we don't understand yet. And that led him to come up with that kind of pejorative but now very fun term, spooky action at a distance. And then later on, someone named John Bell, so this is in the 1960s, he was the first one who came up with an experimental test for this. So for many years, we're like, well, Einstein has his ideas, Niels Bohr has his ideas, and they're very interesting, super important, but we didn't have a way to test them. And Bell came up with a test that one could do where any possible hidden variable theory, as he called it, would give certain statistics, and quantum mechanics would give different statistics. So now all of a sudden we've got a test that we can do. And in the following years, many tests were performed. And in fact, the Nobel Prize in 2022 was for many of the leading experimentalists in those Bell experiments. So today we're looking, and as far as we know, this is what quantum mechanics is. We don't have a way to reconcile that paradox. I think there's still a lot of good theoretical work on that front.
Yeah.
But as far as we know, there is spooky action at a distance.
So there's no real reason to know why that paradox exists. It just exists. Is that kind of what you're saying?
Well, I mean, I would say there are a lot of very interesting quantum theories that try to, again, there's not questions about what happens in the measurements, but understanding what I think even John Bell would call beables, what exists at the fundamental level to describe these. And there's a variety of theories out there. Where we're at, though, is we don't have a way to test them. And so really, where we're at is we have to live in that paradox. Like we recognize that, like, relativity, it makes great predictions. Quantum mechanics makes great predictions, and there's some haziness at their intersection, and there's a lot of great people working on it. As an engineer, I'm really interested in that problem, but that's not what I get paid to figure out. I get paid to use the things that we have been able to establish. So I would say it's still an open question, still a lot of great research. And if people just say, like, shut up and calculate, which is a lot of what quantum mechanics people do, I don't like that.
Yeah.
Even though I perhaps do it. But I think we should keep looking into those problems, but we don't need to wait to use quantum mechanics for useful things.
Gotcha. So quantum key distribution, that's already commercial. Explain what that is and why it matters.
So if we have these two particles, as we mentioned, spooky action at a distance, and we said that a measurement on one particle influences the state of the other particle. And that's completely random. So that's one thing just want to point out. We can't get superluminal communication this way because even though the state maybe collapses instantaneously, we can't control what it collapses to.
Right.
So I think that's an important thing because a lot of people get confused on that. It's like, oh, I can do faster than light communication. You can't do that, but you can do faster than light state collapse. And so the idea of quantum key distribution is that, well, what does random numbers that we're generating at two different locations, what can that do for us? Well, perhaps we can use that as a secret key. For a secret key, I don't really care what the numbers are. This is like a random bit string that I don't want anybody else to know but me, but I don't really care if it's 1011 or 1100. I don't care about that. So the cool thing with quantum key distribution is this quantum randomness, and I'm using an entanglement example. It turns out you don't need entanglement, but I think it's easier to understand with the entanglement example. What if these two parties that are on opposite sides of the world are doing these random measurements? They're generating a secret bit string, and then they could use that to talk to each other, secretly. And there's a few more nuances. You have to do a couple different types of measurements, but when you do that, it turns out you can also tell if somebody's eavesdropping and figuring out your random bits, and that's super important. So you can't stop somebody from what they would call denial of service attacks. So someone could just stand in the way of your light beam and say, sorry, I blocked all your photons. But at least if that's happening, you know it's happening, and it provides a principled way to say, I have a key of certain length that I only know and the person I want to communicate with only knows. And that was really the first main application of quantum information. So quantum mechanics, you should think of it as, this is a theory. This is trying to understand things from a scientific perspective. And then quantum information is let's use that for tasks that we find important, not thinking about physics.
Right.
Just like communication. So quantum key distribution is a way to do that. And in light of the fact, kind of the ironic fact that quantum computers could break our current crypto systems, that quantum key distribution is one of the possibilities to secure our future from quantum computers. So it's kind of ironic, we're find quantum information so I can build computers, hack you, and then we'll do quantum key distribution. But I mean, I'm kind of being facetious there. But it is quantum, let's say, is so fascinating because it does expose vulnerabilities, but it can also protect them.
So I've been with ECE, I think 8 or 9 years now, and over those years, the word quantum comes up more and more and more. So what's changed in the last 5 to 10 years that makes quantum less theoretical and more practical?
If you look at the history of quantum research, I mean, it's been around for a long time. I mean, the standard textbook that people teach for quantum information and quantum computing by Nielsen and Schwang, that was published in the year 2000. And I'm so that's 25 years ago. And some of the technical details there, obviously we've got a lot better physical systems now, but it's still very relevant in 2026. Yeah. So quantum is not new, but I think what has changed in the last few years, I think, is several things. One is I think there is let's say a recognition from industry of its value, and kind of once that ball starts rolling, then a lot of companies need to jump in to stay ahead or to
Yeah.
compete with what's going on around them. And we've really seen that over the last five to 10 years. And what is the big difference there? And for me, it's really the engineering question, because the theory side has been around for a long time, and we know if we had perfect qubits, all the awesome things we could do, but we don't have perfect qubits.
Yeah.
And why don't we have perfect qubits? Well, it's, quote, just an engineering problem. And then, in fact, I think people are realizing it's an engineering problem. It's a really good problem. It's a really important problem. And let's actually fix that engineering problem. Let's solve it.
Right.
So we're really seeing industry get involved. And that, to me, is the big change, because I mean, I love academic research. That's what I love doing. That's what I want to do. I want to push for discovery, but I'm not going to build a product like a quantum computer as an academic. There's just
Right.
the resources just aren't there. And with companies coming on board, it's really pushing the momentum, I think in all directions. And I don't know when we'll have, say, useful quantum computers, and thankfully I don't have to know that answer.
Right.
But a lot of companies are hedging bets on that. But what I am hearing from a lot of people who let's say who I trust and who are not, let's say, not inclined to buy the hype.
Mm-hmm.
There's a lot of people that are thinking this is real serious, and especially on getting quantum computers that, for example, could break our current crypto systems. So really, there's just a lot of excitement there, and I do recognize. I mean, there is going to be ebbs and flows of interest in topics over the years, and so if quantum doesn't deliver in a few years, we won't be hearing it so much.
Yeah.
And as a professor, I don't care. I just want to learn. I want to discover.
Right.
But industry, of course, cares about those bottom lines.
Absolutely.
And so I'm very optimistic that quantum is here to stay, but it might not be. And if so, that's fine. We can find better ways to solve our problems than quantum.
So, do you have an idea? Do you feel like this is something that's going to happen in your lifetime, or is this still decades and decades and decades away?
I think it will happen in my lifetime because of and when I say happen in my lifetime, what do I mean? I mean, we already have useful quantum systems. And
Mm-hmm.
I mentioned quantum key distribution. We have quantum sensing. Quantum sensing is used at the gravitational interferometers today. So we have good, say, scientific applications. We have good security applications for quantum right now. So I want to say that. So really what I mean, are we going to get a fault-tolerant quantum computer?
Yeah.
And I would say I believe it will happen in less than 10 years, but I'm let's say I'm not putting all my retirement savings into those companies. So
Understood.
So that's really where I'm at now. And again, I love it because I don't think it's my job to get the best thing ever. I mean, my job is to explore and to discover and to learn and to pass that knowledge on. And if that learning set comes to the conclusion that actually what I've been spending my life on doesn't work,
Mm-hmm.
okay, I might cry for a while, but I'll move on.
Yeah.
And that's just how it works.
To the next thing. Yeah, absolutely. You've talked about photonic integration being critical. Again, why is getting quantum systems off those optic tables such a big deal?
So when we talk about quantum networking, there's really no way to do it without photons. So photons are single particles of light, and no matter what our qubit system is for doing computing, it could be photons, but it could be many of these other systems, ions, superconductors. Regardless of what those systems are, to talk together, we're going to need photons.
Yeah.
So that means we need to be able to convert whatever information is on our favorite quantum computer and turn it into photons. And right now, a lot of quantum experiments with photons are, like you said, on an optics table. I mean, I've seen some pictures with hundreds of mirrors, and it just makes me cringe when I see it. And the fact of the matter is that is something that if you need 10 graduate students to make it, you can't have 10 graduate students sitting at every node in your quantum network. It's just not possible. And what's really I think exciting is that without really any care or reference to quantum, integrated photonics has been growing over the last few decades as well. So what does integrated photonics do? At its most common level, it's taking advances that we already use for silicon microelectronics and building photonic systems in it. So now your optics table that could be a square meter is now a square millimeter. And those sorts of things are possible. So what that means is now you don't have to have multiple grad students controlling your experiment. You just got to get good chips that you can say calibrate and then calibrate and control. And you could drop these chips into quantum network nodes, maybe in the middle of a cornfield. I mean, who knows? So that I think the photonic integration is a prerequisite. It's not enough. Like if we have perfect photonic integrated circuits, it's not a guarantee that we have useful quantum systems. But I can say we won't have them without.
Right.
And that's where I'm really interested in exploring moving on chip is we're really hitting kind of the limits of what we can do on optical tables. And also even with, I use a lot of fiber optic communications equipment, which it's still on optics table, but at least you have these boxes with optical fibers you can connect it. So I don't have to align all the mirrors, but I still have big components. And we have a lot of losses in those components, meaning that most of the photons you send through them don't make it through. And in classical communications, you just amplify, but you can't do that in quantum. It actually distorts your quantum state. So we think getting on chip is going to be important to get those losses down. And I don't want to paint a rosy picture that like photonic integration is everything, because there's a lot of capabilities we don't yet have on chip.
Right.
But it's why we need to get those capabilities to move forward.
Gotcha. So what's the difference between post-quantum cryptography and what we talked about earlier, quantum key distribution?
Post-quantum cryptography typically is referring to non-quantum solutions to this crypto apocalypse, as I've heard some people say. If you get a quantum computer that can hack, it's called public key cryptography, what we use today, and it's based on the factorization of large prime numbers. So it's based on a mathematical problem that classically we don't know how to solve. There actually could be a classical way to solve, but we don't know. But we do know that quantum mechanics, it's called Shor's algorithm, offers an approach to solve this problem very efficiently. So if we get a quantum computer that's sufficiently large and we can break implement Shor's algorithm, then we can break public key cryptography. So how do we address that? And the post-quantum cryptography way says, well, what if we use different mathematical functions to secure or to generate these keys that we use for communication on the internet? And the nice thing with those approaches is it's a lot easier to do than to build quantum systems. It's much more inexpensive. You're just using computers and mathematical functions. The downside is we don't actually know if that is, it's not provably secure. We just say this is a problem that we think is really hard and we don't know any way to solve it. And we say post-quantum, we don't know of a quantum algorithm to solve it. And we don't know of a classical or quantum algorithm to solve it. But it doesn't mean it doesn't exist.
Right.
Quantum key distribution takes a different approach and really bases the security not on some mathematical problem that's difficult, but rather based on belief in quantum mechanics. So if quantum mechanics is, as a theory, is correct, and as far as we can tell, all its predictions are, then we're building security. We're getting secret keys in a way that is provably secure, that isn't subject to mathematical advances or new quantum computers. So when we think about both approaches, we've got one with like strong theoretical backing, but it's much more, let's say, expensive.
Yeah.
And then we've got another one with maybe less theoretical backing, but much less expensive. And I think both are promising. And if my suggestion is do both, because we need it now. And we need it now because if somebody is harvesting your encrypted data today, if a quantum computer comes out 10 years from now, if you have something today that you care about, not no one finding out in 10 years, and I think we have a lot of personal information that fits in that category, you really want it safe today. And so I think we need to be doing both yesterday.
Yeah. So is there a risk in moving toward quantum computing without preparing security systems?
Absolutely. And I think the I think the cat's out of the bag, so to speak, in the sense that like we know about Shor's algorithm, so people are pushing for it, and so we have to push because everyone is pushing for it, and so we can't just say put on the brakes on that to keep our data secure. So as we're pursuing that, which I do think is a necessity, no matter where what country you're in, you have to try to keep up on that. We will need crypto systems that are going to be secure against that. And the United States is focused more on post-quantum cryptography, maybe a little too negative on QKD, in my opinion, and whereas other parts of the world are kind of looking at both. I just think we don't have the answer, so but we do know we need one.
Right.
So let's push all the possible solutions as far as possible and see what they can do.
So we've been hearing about AI. We had been hearing about it for years and years and years, and now it's here, right?
Yeah.
So is this an AI moment for quantum? Are we there?
So I think really and I'm not an AI person. I wasn't really keeping up with AI, but what was the change? I mean, there's been machine learning AI for so long, but it was really getting AI in front of everyone, right? That was a huge thing, and I think doing it again with like large language models rather than maybe solving interesting math problems, people are like, oh, this is a big deal. So it seemed very big, even though I had been building up for a long time. It just kind of went into everyone's consciousness and day-to-day experience. I think that was the huge change with AI. And so if I look at quantum, I think it's a little bit harder, although not certainly not impossible, but it's a little bit harder to. We're not in the average person's face right now, and I think we can be, but one of the I guess kind of the ironies about making quantum here to stay. It's really we want people to use quantum who don't know quantum, and right now we're not really there. I mean, to really get something useful out of quantum computers, you have to know what's going on right now, because you have to kind of reach at such a low level. So there's a lot of people working on this research. I'm very interested in it as well. How do we get to the level that I can use quantum computers without even really remotely understanding how it works? I can use ChatGPT without remotely understanding how it works. So we're not there yet, but I think it's going to be that moment. It's interestingly enough, it's not really a moment of performance, even though that will be super important. It's really reaching the end user, and for me, I actually think secure communications is that application. I think people understand the importance of privacy, of securing their personal information, and I actually think that's a very compelling application for quantum. That again, we do have those tools here today. It's really a cost thing, why we don't have it laid out more. But that's for me is maybe not as exciting as ChatGPT, but as important. And I think we could be doing more to emphasize how let's say how awesome that is.
Yeah, right.
To enable secure communications in that way.
So you received the Presidential Early Career Award. That was a big deal. What did it mean to you to receive that? So
it was really exciting and honestly very surprising. So I had always heard so I was nominated actually in 2020. So it's a while ago, and it was right after I had earned the Early Career Award from the U.S. Department of Energy. I was at Oak Ridge National Laboratory at the time, and people would float around and say PKs, and it was kind of this mysterious thing. It's like everybody seems to think this is super important, and I hear people talk about it. And I had inclinations that I was nominated, but I hadn't heard anything for years. So I was like, well, that's okay. I mean, I was excited about it, and then I started at Purdue, and then a few weeks in, the announcement comes. I mean, it was super exciting, and I mean, with all that, any award like that, I mean, it really comes down to the support that you have to get there. I mean, for for being, I had a lot of really great support at Oak Ridge National Lab on getting the Early Career Award,
Yep.
which is kind of the first hurdle to then being nominated for the PKs. And so I had really a lot of great support there. And I think that's important because as especially as a researcher, if you anytime that you detract from thinking, thinking hard about hard problems is missed opportunities. And so I think for all these awards, and I mean, your accomplishments are super critical to them, but there's a huge support system that you need around you to get these nominations together, to get these proposals together. And I think that broadly, I mean, that applies to everything. So I'm really grateful for the folks at Oak Ridge who helped with that. And I know Purdue has done a really good job in my time here for encouraging these award nominations and putting those things forward because it is kind of this irony. How do you get the awards? By doing great research. But if you try to get the award, then you lose your research. So you got to stay focused on that research to stay ahead.
Right.
And so you really need that help to get these really exciting opportunities and awards.
Yeah. So you're a Purdue ECE alumnus as well. How is being a student now different than it was maybe when you went through Purdue ECE?
Yeah, I mean, the easy answer, but it's true, is that was before COVID and now it's after COVID. And there is a lot more online opportunities, I'd say, for better or for worse. And so I see very good things about the online abilities because now we have access to a lot of things that we didn't have when I was a student. But I also see downsides. I think and again, it's hard. It's not necessarily easy to articulate, but I know in a face-to-face meeting, I accomplish way more than any virtual meeting can possibly do. And so I think that is one of the big changes and challenges that we have is how to, let's say, leverage online resources without losing the quality of the education, because there is an important face-to-face component. So that is something that I've been navigating now on the instructor side of things. There was never a question when I went to school of like watching a lecture online. You didn't do it. Yeah. You didn't do it. And so now there are a lot of those questions, and figuring out how to, let's say, provide good resources for students, but not provide so many resources that then they learn less because they're not getting the face-to-face interaction. So that's a challenge. But I mean, I think there's a lot of I'm learning it from a lot of great teachers in the department and kind of how to do that. So it's a learning experience for me. I think it's a learning experience for everyone. So we still have. I think there's an optimal solution. I don't know what it is, but I'm working toward it.
Gotcha. Yeah, when I was in school 100 years ago, we had those little tape recorders that you put on your desk and record the lecture and then take notes from it, theoretically. So what advice would you give to your PhD self? If you looking back, what do you wish you had known going through your PhD?
I think the biggest thing is don't dismiss that grad school time. I think and I had a great grad school experience. I mean, honestly, is maybe the best time of my life when I look back on it. But I think there's a sense of like, man, I just want to get that degree and get out. But what I've learned, especially as you get deeper in your career, what you learn in that time in grad school is your base knowledge. And since then, I have learned since grad school. I mean, I'm always learning, but it's just not the same. I could read so many papers in grad school, and you didn't realize how many you could read until you get out and you have all these more administrative responsibilities, and you're not able to do that focus. And so I think to recognize that foundation in grad school, no matter what you do after, no matter what new things you learn, that knowledge that you build there is going to be your toolkit for the rest of your life. And I find myself going back and to so many, even now, I'm glad I still have my notes from grad school. Sometimes I'm like, well, what was this? I remember learning about this. And then I find some slides I had from grad school, and it's great. So I think my big advice is just relish it. It's hard. You're going to have months without getting any results. I think that's another thing to remember, is that research is not like this.
Right.
It's like this, huge. So you can, just because you have months without success doesn't mean you can't have
Success ultimately.
Success ultimately. So I think make the most of that time, enjoy it, learn, build your toolkit, and then have that persistence. Because I look back at grad school, and I mean, this is probably an exaggeration, but I think maybe there were 10 days when I had good data. I mean,
yeah, I know what you're saying.
Something like that. Like
Yeah.
you work, and then you finally get it. And so the point is, most of the time in grad school was failure.
Yeah.
And my advice to students is embrace that. It
Yeah.
is failure, and that's okay. And you don't. The more you see the big picture, and the more you step back, you realize that it was not as bad as I thought it was when I had months,
Right.
banging my head against the wall, not
Yeah.
figuring things out.
Well, it's like every failure is a step towards ultimate success.
It is. That's right.
So when you're not getting us closer to quantum computing, what do you like to do in your free time?
So I really love music, and bass guitar is my main instrument. I wanted to actually go to college for bass guitar,
wow.
and I got accepted to a couple places, didn't get enough scholarship money, so I ended up going into engineering, which I think was a good decision. But I really enjoy playing music, and ironically enough, even though I'm in electrical engineering, I'm not really a gear guy. I just like the music.
Okay.
And the electronic backing is kind of a separate thing. Now that I'm teaching, I'm actually finding more let's say integration with my music hobbies and some of the concepts in electrical engineering, because it is super related. I mean, I play electric bass, so there's all sorts of electrical engineering going into that. So I enjoy that part really about being back as a teacher now. Now I am. For me, they were always kind of separate things, and like here's my work life and here's my music life, but they're kind of coming together now. So who knows? Maybe I could build something useful for music at some point.
Yeah.
But in the meantime, I'll just keep having fun.
That's cool. So Joe, thanks so much for being here today and for such a thoughtful and accessible conversation.
Thank you. Thank you for the opportunity.
So we know quantum technology can feel abstract, but today's discussion makes it clear that it's not just theory, it's engineering in progress. From secure communication to scalable quantum systems, the groundwork is being laid right now. So thanks so much for listening to Engineering Innovations. If you enjoyed this episode, subscribe, make a comment, share it with a colleague or friend, and stay curious about the technology shaping what's next. I'll be back next month with another new episode.